Hello there, and thank you for joining me on this channel, Waters and Stanton video channel. I thought I'd try an intro using the iPhone and see how it works out. I'm not sure what the stability will be like. Anyway, we've still got some summer weather. This is September now, mid-September, and we've got a good spell of weather, so it's a good time to still mess about with antennas. And I want to talk to you about an antenna today that you can make. It so simple to make. You can make the whole thing multi-band antenna if you feel inclined. Now, so many people buy antennas. Nothing wrong with buying antennas because they're ready-made. They should be sort of rugged and last a good many years. But some people like to make antennas, and in fact in ham radio it's one of the few things that most of us are capable of making, an antenna. So I'm going to tell you how to make a very simple multi-band antenna and throw in a couple of tips or dismiss a couple of myths. On the Waters and Stanton video channel, we try to bring you some basic information very often. Information that will enable beginners to get a grip on ham radio, and perhaps those that are more experienced but haven't considered certain things. And on this video, I'm going to talk about a very basic antenna. Basic in terms of how it goes together, but very effective at what you get, the end result. It's a multi-band antenna. It's an end-fed half-wave. Nothing new there, except that I think the way I go about it may be slightly different. It's actually a very simple antenna to make. And if you feel like making something, this may well be something that you should consider, because the end result is quite amazing. It'll handle 100 watts, it'll cover multi-bands, and it's not very expensive to make. All you need is a soldering iron. If you've got a soldering iron, you can make this antenna very cost effective and very effective in terms of the results you get. So let's take a look first of all at what you need to make this antenna. Right, the first thing you need is a ferrite core. I favour the 240-43 ferrite core. It's large enough to work with easily, it'll handle 100 watts, and it's readily available in the UK. It may cost you £6, £7 or £8, but that actually probably is the most expensive part of this antenna. Next, you need a gash bit of flex or wire or string, about a metre or so long. Come back to that in a minute. You need some tinned copper wire. I use something which I think is around about 16 gauge. I'll put a close-up on the screen of the RS components number that I use, but anything that is tinned copper and is reasonably, I say thick, diameter about 16 gauge. I suppose you could go down to 18, but I think mine is around about 16 SWG. It's not critical, it just needs to be fairly stiff so you can wind it and the winding will remain in place on its own. Then you need a capacitor, a 100 picofarad capacitor rated at about 1 kV. If you can't find something rated at that voltage, then get a couple of 220 picofarad capacitors, put them in series, and you'll have 110 picofarad, which is basically the same as a 100 picofarad capacitor. We're not talking about critical capacitors here. And finally, you need some antenna wire. Any wire that is conductive will do. I favour PVC covered wire. You can go down to your hardware store. You need 20 metres, because I'm going to concentrate on an antenna that covers 40 through to 10 metres. So you need 20 metres of flex. You could get 10 metres of twin flex and pull it apart, join it together, and you've got 20 metres. You may have your own ideas. Anyway, you need 20 metres of some form of antenna wire. And that basically is all you need. Let's sketch out the basic antenna. End-fed half-wave. It's basically a dipole. It's a dipole without a break in the middle. So it's a half wave length on 40 metres, which means to say that it's 20 metres of wire, approximately. Come back to that in a minute. We need to feed it. That's a high impedance there, and that is a high impedance on harmonics as well. So on 40 metres it's a high impedance. It's high impedance on 20, 15 and 10. That means to say we've effectively got a constant impedance whatever band we operate on. So we need a transformer. And the simplest transformer is what is known as an UnUn, and we're going to use a 49:1 UnUn. So basically the UnUn that you'll see drawn on diagrams is something like that, with a coupling coil there. Those two go down to earth, and the coax feed goes to that point there, and the outer sheath of the coax goes to that point there. So that's the input from our transceiver, that's the coil output to the antenna, and it's a 49:1 ratio. Now we can make that somewhat simpler. Right, instead of using the coupling coil that we had before, we're going to make things a lot easier. We can have a coil which will be fed round on the ferrite core, and that we'll call earth, although it's actually not earth, it's negative. And we're going to feed the coil, instead of inductively coupling, we're going to direct couple using an auto transformer method, like that. And the outside braiding of the coax will go to that point there, the negative side. The inner conductor will go to a tap point there. We'll tap 2 turns up from the bottom of the coil, and the top of that coil there will be feeding the antenna. That makes the whole thing somewhat simpler. Now believe me, making this transformer is remarkably easy. It perhaps looks more complicated on paper than it is in practice. But before we come to that, I just want to talk a little bit about the 49:1 UnUn and so forth. You might want to skip this bit, you may want to listen to it. The end of a half-wave antenna is a high impedance. We all agree on that. What we don't know is actually what that impedance is. It can be anything from around about 2,000, 2,500 up to around about 4,000. We just don't know. But the 49:1 UnUn was designed because we make an assumption that the feed impedance is around about 2,500 ohms, and 49:1 enables us to match 50 ohm coax to 2,500 ohms. But as I say, we don't know exactly what that impedance is. It's going to vary from antenna to antenna because of location, situation and so forth, and what's surrounding it. Some have experimented with a 56:1 and even a 64:1 in the hope of getting a better match. Well, you may get a better match depending on what the actual impedance of that half wave is. But bear in mind that the characteristic impedance of a centre-fed dipole is around about 70 ohms. We quite happily feed it with 50 ohm coax cable because that's all we've got. We can't vary the impedance of the coax cable. So we've got a mismatch there, but we don't worry about that mismatch. It doesn't make that much difference. And the same really goes for a 49:1 UnUn. Whether it's 49:1 UnUn or 56:1 or even 64:1, it's really going to make very, very little difference. You may get a slight improvement in VSW or you may not. Now, another thing to remember is that when you attach a UnUn, a transformer, a 49:1 UnUn or any other matching unit to the end of a half wave, you effectively lower the Q, and you probably lower the impedance slightly as well, because the end of a half wave is very, very sensitive to anything near it. So what actually happens is when you attach the transformer to it, you almost certainly lower the impedance somewhat. You certainly lower the Q. you actually get a better bandwidth. And when it comes to the actual impedance, it really doesn't matter what that impedance is, whether it's 2, 2.5, 3, 3.5, it really doesn't matter. That 49:1 UnUn will match it. So don't get too worried about what relationship you should have, whether it should be 49:1, 56:1, even 64:1. The industry standard has basically settled on 49:1, and that works quite well. Now let's talk about winding the coil. We need some tin copper wire. We don't know how much we need, and if we pull off too much, then we're going to waste some wire. So I always, first of all, get a bit of gash wire. This is PVC wire, and just wind it around. We're going to go for 14 turns. We need 14 turns on this core. So what I do is I wind round 14 turns on this core, and once I've wound 14 turns on this core, I know how much wire I actually need because I can measure it. Right, I've wound 14 turns of this flex onto the core. Because I'm going to spread it around a bit, and because the wire, the tin copper wire, won't probably sit so snugly, I'll give an extra bit. So probably around about there is enough, and I'm going to cut that with the wire cutters now. Now, believe it or not, it measures almost a metre. I need a metre of wire for 14 turns on the ferrite core. So I've measured off my 1 metre of wire, and let's go this way actually. Bend it there, that's one end of the coil. And what we're going to do now is to basically bend this round, get it as close as you can to the ferrite core. It's a little bit fiddly, but it's not difficult. And because this is, I'm not sure, I said 16 gauge, this might be 18 gauge actually. But anyway, it doesn't really matter. And because it's semi-stiff, it stays pretty well in place. Now, you may have noticed on some of the construction YouTube channels, in fact a lot of them, they advocate crossing over the wire at the halfway point. We'll put in 14 turns on here. In actual fact, it's been proved that that doesn't make any difference whatsoever. So we're just going to go for a straight winding. And I've got this upside down really, but basically that will count as the first turn, that will count as the second, that's the third, that's the fourth. So we're going to carry on, and we're going to put 14 turns on here. Now, we're using tin copper for a very good reason. It's so much easier to solder than to mess about with enamel copper wire when you don't have to. You can put tin copper wire straight onto the ferrite core. You don't need any insulation or anything like that at all, because the core is non-conductive. You don't believe me? Put an ohm meter on it. And spacing, well, obviously because we've got fairly wide spacing, we don't have to worry about short circuits because that's not going to happen. And we keep winding this anyway until we've got our 14 turns on the core. And here's our finished coil. Now let's just explain these windings because it can cause confusion. That point there where the wire starts, we can regard that as 0. So our first complete turn is there, that one there. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. That turn there, technically, I suppose, should finish there. So we've probably got 14.5 turns, but for the sake of construction, I normally take it out there. So there we are, that's the coil. It's very simple to wind. It's self-supporting, or it's self-fastening on the core, so you don't need anything. Don't try to fasten it with anything if you put plastic tie wraps around, because sometimes that core can heat up a bit. So you don't want anything there and there. You could, if you wanted to make it really neat, use what they call plumber's tape, which is a white tape you'd get at the local plumbing shop. I'm sure that B&Q and all the other places do it. And that you can wind that around there. It makes a nice, neat job of it, but it's not absolutely necessary. So that's, for example, let's assume that's going to be the aerial. So that's going to be the input. Now we've got to make a tap on the second turn there, and that will be the point at which the inner conductor of the coax joins the coil. The outer conductor of the coax will go on that one there. We could do it the other way around. It doesn't matter which way which is input, which is output. But for this purpose, I'm going to say, okay, well that's my input. That's going to be my negative side, which the coax sheathing goes to, and the inner conductor is going to go onto the second turn, which is that one there. Now we've got one side which is longer than the other, which is quite convenient because we're going to use the excess on that side to make a link on that side. So we snip a bit of the excess wire off here, about there, and cut it. And what we're going to do now is we're going to bend this round and solder it onto the second turn of this coil, and that will be the input for the coax cable. The earth side of the coax cable will go on there, and the inner conductor of the coax cable will go on there. Now what we need to do, we need a small screwdriver to put under this here. We just bend it slightly. The wire will give slightly, and it will just give us enough room to get this bit of wire under there. There we are, it goes under there. And what we're going to do is bend that round with a pair of pliers so it grips it, and then we'll solder it. Now you can see now that this wire has been bent round there. We've just got to solder that and just cut a bit of excess off on this bit here. And there we are, that's the coil or the toroid soldered. We've got the low impedance input there, and we've got the high impedance output there, which goes to the antenna. All we need to do now is to solder a capacitor across there. That will improve the HF performance of the UnUn. And there we are, that's the finished UnUn. Just need to trim that off there, and we're ready to go. So what you now need to do is to connect your antenna to there. You can use a bit of electrical joining block or something like that. You could use the same here, electrical joining block. You could solder a piece of coax directly on there. That is the negative side, the sheathing side of the coax. That is the centre. And put it in a box, or you could connect it to terminals, whatever. The great thing about this is that will work as an UnUn and give you, it'll work on 80 as well if you have the longer end fed halfway, but if you have a 20-metre length of wire connected to that and you have the coax connected to that in some way, then you've got a multi-band antenna. One other thing that I will comment on, because I'm sure I'll get questions otherwise, is do I need a counterpoise? Do I need an earth? The answer is no, you don't. You don't need a counterpoise. You don't need an earth. All you need is a coax cable going from that UnUn back to your transceiver, but make sure that you have a line isolator just before the coax goes into the transceiver or into the VSWR meter, whatever is the first bit of gear it meets in the shack. Make sure you've got a line isolator there. That will help you get a decent match on the antenna, because otherwise there will be RF currents flowing down the outside of the coax, common mode currents we call them, and that will upset the VSWR readings and possibly upset the internal ATU in the transceiver. But no, you don't. I've done many tests on this. You will hear people say you do need a counterpoise. You know, in the main, they either have never tried the antenna, or they've been told that you need a counterpoise by somebody else. The fact is that all the tests I've made, there's not a hape of the difference if you use a counterpoise. And Les Moxon G6XN covered this actually in quite a few years ago with NFED antennas. You need call it a counterpoise, whatever you like, you need 0.05 the wavelength of counterpoise or coax cable at the end of that antenna. Now 0.05 of a wavelength is very small. It's just a few feet, even on 40 meters. So whatever length of coax you're going to use for that, to connect that antenna, or that UnUn rather, to your transceiver, it's almost certainly going to be longer than 0.05 of a wavelength. So no, you don't need a counterpoise. Now, as far as the length of the antenna is concerned, you want to start off with 67 feet or 20.4 meters of wire. Almost certainly that will be slightly too long, but it's better to be too long than short. And then what you do is you check the VSWR on the 40 meter band, and you want to try and get the resonant point fairly low in the band, say around about 7.075. And you can very easily check the resonant point by doing a VSWR check at the bottom and the top of the band. If the aerial's too long, you might find that the lowest point is at the bottom of the band, and it's possibly just outside, the resonance is just outside the band, perhaps on 6.9 megahertz. So trim a bit off the antenna, do it fairly steadily. I would say probably 3 inches, something like that, whatever that is in centimetres, say 5 centimetres, perhaps a bit less than that. You don't want to over trim. Alternatively, what you can do is just fold the end of the wire back on itself, and that will also shorten the antenna. And you want to try for resonance around about 7.075, or maybe even 7.05. If you've got resonance there, then check the VSWR on the other bands, because what you'll find is that on the harmonics, the resonant point will not be a direct harmonic relationship, it'll be slightly higher. So if we have 7.05 on 40 meters, we would expect 14.1 on 20 meters, but it may well be 14.15 or 14.175. It gradually creeps up. On the 10 meter band, you'll probably find the resonant point is fairly high in the band. It could be near to 29 megahertz, but it'll be broadband, so don't worry too much about that. It'll be broadbanded, and your internal antenna tuner will match it anyway. So you should get good coverage on the 4 bands, 40 meters, 20 meters, 17 and 10 meters. Now what about the walk bands? Well, I've always found that you can actually get this antenna to actually work on the 17 meter band, 18 megahertz, and the 12 meter band, which is 24 megahertz. You can actually get it there. Now, you won't have a very low SWR, but I've always found that the internal matching unit in my transceiver will actually match it. You will probably get a little bit of heating up in the transformer, and you will find that you're losing perhaps a dB or a couple of dB, but it still works. So if you want to try that, do try it. You'll probably find it'll work, and you'll probably get some good contacts. I've had some pretty good contacts on the 17 meter bands. Even though the SWR is around about sort of 3 or 4 to 1, it still works okay. So there we are. So I hope that's been of interest to you. It's a way of making a multiband antenna quite cheaply. As I say, the most expensive item will probably be the ferrite core. You can get capacitors, by the way, from Amazon. They do 1 kV capacitors, so you can get those from Amazon. In fact, you get a whole pack of capacitors from Amazon. As regards the tin copper wire, I haven't checked, but I think Amazon will do tin copper wire as well. So if you you may have your favourite source of course of getting the wire, but it's a low cost way of producing a multiband antenna. Now, as regards packaging it, well, that's entirely up to you. I have actually used this sort of antenna with the UnUn just inside the window of the house. I've put that just had that hung in from the window with the coax connected to it, the arrow connected to it, threaded the wire through, or jammed the wire through the side of the window, run it down the garden, and that works fine. Works okay. So I hope that's encouraged you to do a bit of home construction, and it's as I say, it's very simple. It works. It'll handle 100 watts with no problem at all. If you want it to cover 80 meters, then you've got to double the length of the antenna. But I think a lot of us haven't got gardens long enough for that. So there we are. Thank you for your support on this channel, by the way. Thank you for all the orders that we get, both on the phone and on the website. Much appreciated. And we do try to give you a good service, and we try to return some of what we get from you in terms of your buying things by publishing these videos. And as I say, I try to sort of give you some idea of sort of cutting the cost of amateur radio down, doing a bit of experimentation, doing a bit of home construction. So there we are. Thank you for your support on this channel, much appreciated, as I've just said already, I think. And as usual, I'll look forward to seeing you in the next video. Bye for now.